Welcome. In our next lesson here in week 3, we're going to look at measures of variation. So when we're looking at a list of data, we want to know, how does it vary? So one of the first things we'll look at when we look at variation is we look at the range of data. So let's take the range of data that we worked with in the last lesson. We had a set of data. And let me go grab that set of data. And here's where we calculated the median. So I'm going to grab this set of data, and it's going to disappear for a minute while I grab it. And I'm going to go back to our range slide. And let's paste this set of data right there at the bottom. Get rid of that. If we look at this data, what we're going to see is that we have a largest data value, which is our max, is 97, and our smallest data value, which is our min, is 66. So if we want to calculate the range of our set of data, this gives us an idea of the spread. The range of our data is our maximum data value minus our minimum data value. And in this particular case, let me grab this, copy it. In this particular case, you can clearly see that our max data value is 97 and our minimum data value is a 66. And when we take the difference, we end up with a 31. So 31 is the range. It's the spread of our data. It goes from 31, from 66 to 97, which is 31 unit spread. That's our range. Now another way of looking at the variation of our data, this tells us the range. One way to look at the variation is to look at the standard deviation. So we could look at the standard deviation of both a population, that's an entire population, or a sample of the population. Usually we look at the sample of a population. Populations do tend to be large. So when we look at a population and we want to find the standard deviation, we use sigma. And for a sample standard deviation, we use S. Now the formula for the standard deviation is equal to the following. It's very similar. It is the square root, now they're both square roots, of a ratio. I'll draw a ratio bar. And the denominator of our population standard deviation, we write n, where n is the number of values or the size of the population. So we could say n is the size of the population. And for our sample standard deviation, we have little n, which is the size of our sample, minus 1. So there's a slight difference there. Okay. In the numerator of the population standard deviation and the sample standard deviation is very similar. They both are summing up a set of values. And they're summing up a set of values that are squared. And the values that we're summing up, that are where each one is squared, is the difference between each value in the set, whether it's a population or a sample. So that would be x minus the average. So in our sample, it would be the average of our sample size. But when we're talking about our population, we take our population average, which is mu. So there's our standard deviation. Let's make sure that we have an understanding of this. Now, underneath our population, n is equal to the population size. That's the population size. And our sample, n, little n, is our sample size. In our population, mu is our average value, or I should write mean, which means average. That's our mean, the average for the population. And x bar is the average for the sample. And of course, mu, actually that's sigma, excuse me. Sigma, written this way, is our standard deviation for the population. And S is the standard deviation. I'm just going to copy that. S is the standard deviation for the sample. Now, it's generally difficult for us to find the population size. It's the average of the population and the standard deviation of the population. That can be challenging because populations are very large. So for this reason, we tend to use standard deviations or find standard deviations for our samples. And the samples are samples that we will randomly pull. We should randomly pull these samples from our population. So we're more likely to use this formula. And given we find the average value, that's the first thing we want to do. We find our average value in our population. We look at the size of the population, and with this information, we calculate the standard deviation. Now, I'm going to show you how to do this, but I want to make you fully aware that you can use both Excel and also the TI-83 or 84 calculator to find the standard deviation. So don't panic if you look at this and think, oh, this math is really complicated. We have software tools that take care of it for you, but for those of you that are interested in finding the standard deviation on your own, I'm going to do that in the next slide. So let me add a page below, and I'll show you how to find the standard deviation. Now in this particular case, I'm going to use a set of values, a very small set of values, just so that it makes our calculations easier. I'm going to say, let's imagine that n is 3. That's my sample size, okay? And my set of sample data is maybe 3 test scores, okay? So the first value is 78. The next score is an 80. And the next score is an 82. Our mission is to find the standard deviation. Well, if we look back, let's just look back at that page. The first thing that we needed to do was to find our sample size, and we did that. Okay, so now our next thing is we need to find the average. The average. Now we've found the average before if we look back on our previous lesson when we found the mean. Here's the mean. And if you see here, the mean is the sum of all your x values divided by the number of values. So we'll copy that formula. And let me go back to where we left off, which is here. And let's put our formula in. Okay, so we're going to find the mean. So what this is telling us to do is to add up our values. So we have the 78, and to that we add an 80, and to that we add an 82. So these are our three values, and this is a very small sample, and small samples are actually not a good idea. The purpose of this is just to show you how to calculate the standard deviation. So our sample size is 3, and if we add these up, we end up with 240. Okay, if we add these up, we have 240, and if we divide this by 3, we will find that our average value is 80. Okay, so we have n, the sample size. We have 80, which is our average value. I'm going to go back. And looking at our formula, that's what we need. I'm looking at the formula that we're using here for standard deviation is we need n and x bar. And of course, the x represents our x values. So let's go back and start this calculation. Our standard deviation is equal to the square root of the sum of a set of values that are squared. This set of values are each one of our x values minus the average value, and then the entire thing under the radical here in the denominator of this fraction is n minus 1. So let's work this out. I'm going to move this down. It's looking like it's a little close to the work above. Okay, so what do we have here? Let me make this a little neater here. And I'm going to draw our bar. The denominator is simple. It's 3 minus 1, right? In the numerator, we're going to add up a bunch of values that are squared. We need to add up, there are 3 of them. Continue this on. Okay, so the first one is our x value is 78. Right? Our second x value is 80. And our third x value is 82. From each one of these, we want to subtract the average. So I subtract 80. I'm going to move this over a little bit. I seem to be falling off the page a bit. There. From 80, we'll subtract 80. That's easy. That's 0. And then from 82, we subtract 80. Let's scratch that out. This is squared. Okay. So let's continue this on. And what we end up with in the denominator is 3 minus 1 is 2. And in the numerator, I have a 78 minus 80. That's a negative 2 squared. You're going to notice because each one of these is squared, we lose the negative sign. Because if you square a negative, it becomes positive. We have 0 squared. And then the last one, 82 minus 80 is 2. So we have 2 squared. And let's finish this off. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4. And this is all divided by 2. So this becomes the square root of 8 divided by 2, which is the square root of 4. And the square root of 4 is 2. And here we have S, which is the standard deviation of our very small sample. Now, you can imagine that if you had a larger sample, and larger samples are certainly more appropriate for doing statistical analysis, and if you had a larger sample, this would be a fairly complicated calculation. So it's important that you have an idea of what's going on to calculate the standard deviation. However, You can use software to do this, all right? Now, let's take a look at, we're going to look a little closer. Standard deviation gives us an idea of the spread of our data throughout the range. And there's another indicator of our variation, and that is the variance. Now, the variance is equal to the, let me go back to standard deviation for a little bit. Let's take a look at the formula for standard deviation. Let me highlight this. This is the formula for standard deviation. So the variance is the square of the standard deviation. It basically would mean don't take the square root in this equation. And so the variance in this particular case is, which is written as s squared, the variance, we'll go back. The variance in this case would be 4. So let's take a look. So variance, when we talk about variance, we say it is equal to s squared. That's how we write variance. It is the standard deviation squared. Or, if we're talking about a population, it's sigma squared. Okay, so let's make sure that we have this straight. This is how we write variance. This is how we write variance when we're talking about a sample. And this is how we write variance when we're talking about a population. And again, we don't usually calculate variation for a population because it's generally too large. So the formula for the variance is equal to s squared, is s squared, that's how we write variance, and it is equal to the sum of the set of the following values squared, and that is each x value in the sample minus its average, so the difference squared, divided by n minus 1. And if we're talking about a population, the population variance is written this way, and it is the sum of, that means adding up, all the sets of data that are squared, and these are each population value minus the average in the population, divided by capital N, which is the size of the population. So basically, the variance for any population or sample is simply equal to the square of the standard deviation of the population or the sample. Now, there is a range rule of thumb when we're looking at data. In the range rule of thumb interprets a known value for the standard, interprets if you know, let's say that you know, you have a known value for your standard deviation. Well, you can use, it's kind of a crude but simple tool for understanding standard deviation, and it's called the range rule of thumb, which is based on the principle that for most data sets, and that would be a fairly large data set. In our case, ours was a little too small. I only made it small for our calculation purposes. So the range rule of thumb, which is based on the principle that for most data sets, the vast majority, about 95%, of the sample values lie within 2 standard deviations of the average, or the mean. So if you know the mean value, you know that about 95% for most data sets, 95% of the value fall between within 2 standard deviations of the average. Okay, so let me give you an example. If we know the average, let's say I know that the average value in a set of scores is an 80, and I know that the standard deviation is 5. Well, let's take a look at what this means. If this is 80, and of course that's our average, or mean, if we move 1, 2, 3, 4, 5 out to 85, we've moved a distance of 5 units, which happens to be the standard deviation. In other words, this is one standard deviation. If we move out 1, 2, 3, 4, 2 standard deviation, that brings us to a 90. Now if we head to the left 5 units, then we go 1, 2, 3, 4, 5 units to the left, and this brings us to a 75. Well, that would be -1 standard deviation from the average. Here's 0 standard deviation. In other words, we're sitting right at the average. We haven't deviated at all, okay? But here now we've deviated. When we get to -1, we've deviated 5 units to the left, which is -1 standard deviation. We went down 1 standard deviation. That's 75. And if we go down another 5, so that we're at to the left 2 standard deviation, 1, 2, 3, 4, 5, that brings us to 70. And we would say now we are -2 standard deviation to the left of the average. Or we could be +2 standard deviation. And for most sets of data, if most sets of data fall, the entire sample size would fall in this range from 70 to 90. If we know that the average is 80 and the standard deviation is 5. Most of the data, when we talk about it, not about 95% of the data will fall between 2 standard deviation below the average and 2 standard deviation above the average. This is part of the range rule of thumb. And another way of looking at the range rule of thumb is you can estimate, let me add a page below, you can estimate the standard deviation based on the range. So if you know that, let's say you know the range is 20. If you know the range is 20, then you can estimate that the standard deviation is approximately equal to the range divided by 4. And that would be 2 above, 2 standard deviation above, and 2 standard deviation below the average. So in this case, if our range of our values are 20 and we divide by 4, we get an estimated standard deviation of 5. So this is also part of the range rule of thumb. Moving forward, we're going to look at now what is called the empirical rule. The empirical rule works for data that's distributed normally. And when I say distributed normally, if we were to look at the data, it tends to be bell-shaped, like this. And that would be, let me put in, if we created a histogram, as we did in our previous last week, this is an example of a histogram that's normally distributed. If you look at this histogram, it's shaped like a bell. And we consider bell-shaped histograms to be normally distributed. So this is more or less normally distributed. It's close. So we have something that's distributed fairly normally, and this is an example of a normal or bell-shaped curve. Let's write that down. This is bell-shaped, and if our data, problems with my stylist. Bell-shaped or normal. And this is a normal distribution. And when we have something that's a normal distribution, we can use the empirical rule. And the empirical rule is what we call, it's the 68, 95, 99.7 rule. And what this rule tells us, I'm going to use red here, is let's go back up to this set of data. And we have different classes, and let's imagine that our average is right here. And let's say we're going to move out to the right one standard deviation. So this value would be whatever our average is plus one standard deviation. And we'll move out again so that this is our average plus 2 standard deviation. And then we'll take it out here and say this is our average plus 3 standard deviation. And then if we do the same thing, we go to the left. 1, 2, 3. So this is our average minus 1 standard deviation. This value here on our x-axis would be our average minus 2 standard deviation. And over here, this last one, this value of tick mark is our average minus 3 standard deviation. So, well, let's draw some lines here. There's our average. This line represents 1 standard deviation to the left of the average. And then this line is going to represent 1 standard deviation to the right of the average. So what this means then is if this is the average, all data that resides within 1 standard deviation to the left or the right of the average, that would be 68% of our data. Now, if we wanted to know, what about all the data that resides between 2 standard deviations above and 2 standard deviations below? That would be 95% of our data. So I think what I'm going to do is let me grab this. I'm going to grab this, and I'm going to copy it. And I'm actually going to resize it. Maybe it disappears while I... Okay, let me resize it. I'm going to make it small. I'm going to want to put 3 of these here. So I'm going to make them sort of small. Here's 1. Okay, and there it goes back. And then I'm going to put another one to the right of it. Too large. Let me copy this again. I'm a little bit stubborn here. Let me copy it. Okay, it's back. And paste it. So I want to put 3 up here. And paste another one below. Okay. So this is our 68, 95, 97 rule. Let me move this. Move it over to the side here. So 68% of our data is going to fall, 68 up here, is falling with the, between 1 standard deviation above and 1 standard deviation below our average. Now over to the right, I'm going to extend this to include all the population that's 2 standard deviation below and above. And in that case, let's zoom in on this. It's not going to be 68. Let's get rid of this 68. Okay, let's fix that. Refill it in. Okay, so this is going to be 95% of our data is going to fall within 2 standard deviation above and 2 standard deviation below our average or mean value. So we'll put the 95 up here. Paste. There's the 95%. And then finally, the last case, I'm going to get rid of the 68 because it's not going to be 68. Because in this last case, let me get to erase the 68. And I want to go 3 standard deviation to the left of the average, which brings me to here, and then 3 standard deviation to the right of the average, which brings me over to here. And that is going to give me 99.7% of all my data values in my sample. And so this is the empirical rule. So it's very handy. We're going to be looking at normally distributed data sets. And this is an important thing to part of statistics is knowing, and this is a pretty amazing rule, is that we can pretty much guess or use statistics to find the probability that something will lie within 1 standard deviation or 2 standard deviation, that's to the right or the left of the mean, or 3 standard deviation to the right or the left of the mean, because we know in a data set that 68% of a normally distributed data set will lie between 1 and 2 standard deviation above or below the mean. We know from the empirical rule, if our data is normally distributed, that 95% of our data set will lie between 2 standard deviation above and below our mean. And then finally, just about all of our data, 99.7, and that's quite a bit of data, will lie between 3 below our average or mean and 3 standard deviations above our mean. Now sometimes we have outliers, and these are values that really, for some reason, there's a problem with them. They don't belong there. And they would not fall under the empirical rule, or they would be our remaining 0.3% of data that falls outside of the 3 standard deviations above or below the average. So this concludes our week 3, lesson 2 on variation.